So we're starting section 4.4, the shape of a graph. And we want to discuss concavity and the second derivative test. So let's talk about concavity and what does it mean about the direction of the graph, increasing or decreasing, and concavity together. So if you break down a circle into four pieces, one piece over here, and the other piece over there, and the other piece over here, over here. You can notice then that the one up here is sitting below the tangent line, so it's concave down, and it's increasing. The piece over here is sitting below tangent line, therefore, and it's concave down, and so it's decreasing and it's concave down. Below the tangent line is the concave down. These two pieces on the bottom are concave up. One of them is decreasing, the other one is increasing. And so these four options are the options that you have that are relative to the direction, increasing, decreasing, or concavity up and down. Now, how do they relate to f prime and f double prime? When a function is concave up, that means that f double prime is positive on that interval. If a function is concave if a function is concave down, the second derivative is negative. F double prime is negative. If function is increasing, f prime of x is positive. If a function is decreasing, f prime of x is negative. So now match all these, increasing and concave up. So concave increasing means you have to put a increasing piece of tangent line. Then concave up means that the function should sit above the tangent line. Increasing and concave down. So again, tangent line should go direction in a positive direction up, and concave down means piece is underneath. And similarly, decreasing tangent line, then you put a piece of the function above it. That go a little below, but I meant to be above. Again, tangent line decreasing and below because it's concave down. And so again, with the information that you have, and usually you start with the tangent line, then you, according to the concavity, you decide which of these pieces you choose. Basically, for example, in this row, I decide according to f prime bigger than 0, the tangent line will look like this. And then I decide by the concavity. For this row, according to the tangent line being negative, in the direction decreasing, I'm going to go put the tangent line in, and then concave down goes below, concave up goes above it. And that's how I choose the shape of the graph. Now, let's do a few examples. Example 1, the function f records the temperature in degrees Celsius. Recorded 3 hours after the sunrise. At 3 hours after sunrise, you're uncomfortably hot. So I'm hoping that it's not going to get hotter, but I may not be that lucky. How do you feel about each of the following scenarios? So f prime of 3 is positive, it's equal to 2. That means that then if I draw the tangent line, it looks like that. Then I will have, and then it says f double prime of 3 is 4. That means it's a positive value. So the piece of the function is going to sit above the tangent line like that, right? And so this is like increasing, the temperature is increasing and fast. Oh, scenario A is bad. Let's go to scenario B. Scenario B says f prime of 3 is negative. Oh, I like that. F prime of 3 is negative. And then f double prime is positive. So basically, if the function is sitting above it. And so it's decreasing, but it's gonna kind of and eventually not go sharply. Then I have the option that goes f prime of 3 is 2, and then f double prime of 3 is negative 2. So it's right here. This is a better option than A, worse option than B, because still increasing, but it's not increasing as sharply as A did. That was the worst option. And then the fourth option is decreasing, because this is negative, and then we have this, so it's sharply decreasing. I like this option. That's the one that I want. It's not only it's decreasing fast. And so that's how you know how to treat your functions, basically. And I click at question 1. According to the Guinness, I click at question 1. According to the Guinness Book of World Record, the largest cookie ever baked weighed 40,000 pounds and had a diameter of 101 feet. Let f of t be the temperature of the cookie t minutes after it came out of the oven, very large oven. What does the graph of f look like? So stop the video and try to answer the question. Now that you're back from stopping the video, hopefully, let's try to answer the question. So some of you may know the Newton laws of cooling, and so this follows the Newton's laws of cooling. But let's say T and F of T. And so let's say this is the room temperature. Let's say it's 75 degrees Fahrenheit. And so when we take it out of the oven, it's pretty hot. And so it's going to be up here somewhere. And it cools down, but it doesn't go under the room temperature, does it? So it sort of settles over here. So this is, and so what happens is that when it's very hot, that's the Newton laws of cooling, when it's very hot, and the difference between the cookie and the room temperature is high, it sort of cools down faster, and then it cools down slower when the difference is smaller. And but anyway, even not knowing that, I just know that it's not going to be cooler than the room temperature. It's going to kind of bend this way. So it's going to be decreasing, but concave up. No, sorry. Decreasing, but concave up. And that's B. And so now, and the other thing is that this looks very familiar to you. This looks like basically the graph of the function looks like A plus B e to the power negative CT. It's like the exponential function that works that way. And a lot of these things are exponential functions. A lot of real applications of calculus, they end up with being exponential functions. That's why the exponential functions are so important. I got a question 2 of section 4.4. And when a skydiver initially jumps from the plane, the only force acting on her is gravity. As she falls faster and faster, air resistance increases and counteracting the effect of gravity until she reaches terminal velocity. So again, this one, so it's telling you speed, so it's not velocity, so it's not a negative value, it's a positive value, right? So speed and time, s of t, and s of t, I know there's a terminal velocity or terminal speed here, and then what is happening is that the skydiver starts from 0 down here, and then it just the speed goes higher and higher, but doesn't reach that because of the air resistance. It kind of gets it's still increasing, right? But it's increasing a lot slower, slower. The rate of increase is slower, basically. And so this is increasing and concave down, increasing and concave down. And again, this looks like and which it is, it looks like an exponential function, and it looks like that, basically.